Hey astronomy kids, Mr. Johansson here. We're talking galaxies. Galaxies. This is a freak show. When you were a kid, if you were being cute when you first learned about space and stuff, and you were putting down your address and you said such and such a street and your town and then New York State, and then you said, and USA, and then you said, planet Earth, and then you said the solar system. Well, what's the next thing you put on the address? You go from solar system around our star to Milky Way galaxy. Are you kidding me? There are so many stars in the Milky Way galaxy. You'd think we'd have subunits, but we really don't. We are in orbit around all the other stars making up the Milky Way galaxy. So, we want to look at the galaxy, look at the size of it, which is mind-boggling. I could do a diagram, but there's no way I could get it into your head how big this thing is. We're not set up for it. I can think of how far it is, someplace I might walk, someplace I might drive. You can even think how far it feels to fly someplace, that it feels really distant. Our brains cannot handle the distance in space. Not set up for it, really no need for it until we start doing astronomy. Then we let math do it, but look at this diagram. This, I give you, our galaxy. And these are all the important numbers within that. So check this out. Galaxy, this is seen edge on. And I'll show you another diagram seeing the galaxy face on, right? Edge on first. This would be the stars we call the bulge of the galaxy. The bulge. Okay, so we'll call that the bulge. And different galaxies have different sized bulges. This then extending out on each side, that is the disk, a very different population of stars. The disk. Going across the whole disk, like it says here, 100,000 light years across the entire disk of our galaxy. Whoa, okay. But the disk itself is only 1,000 light years thick, 1/100th the size across it. So the galaxy seen edge on, the disk looks very thin. But try to understand something. As thin as that looks, to go from here to here would take 1,000 years for a beam of light. I hope you find that mind-boggling. 1,000 years for a beam of light. Did you hear the bells go off when I said that? It's freaky. Yeah, like when you look up or down out of the galaxy, which you could do on a starry night if you're not looking at that Milky Way, you're looking up or down out of the galaxy. The stars on the disk, most of them are so distant that you can't even see them, even as thin as that disk is, supposedly. 1,000 light years. All right. If we look over here, I have shown you how far it is for us from the center of our galaxy. Now, the center of our galaxy, that is one crazy place. There is a 4 million mass black hole, a supermassive black hole in the center of our galaxy. Indeed, they do believe there is a supermassive black hole in the center of most, if not all, galaxies. A black hole of that size, the event horizon is about as big as our solar system itself. And remember, that supermassive thing, 4 million masses, 4 million times the mass of our sun. 4 million. How big is that actual object? Infinitely small and still collapsing. Crazy. But astronomy, isn't it awesome? So these are the major ideas of it. You are on a star here, one of 400 billion, some estimates range up to 1 trillion. Over your lifetime, we'll probably refine the estimates a little bit more. But see these dots here? These show one more population of stars. So we have the bulge, we have the disk, and they are very different populations of stars, I'll show you. But then we also have this grouping of stars that loosely forms a spherical object around the galaxy, and these would be called the halo stars. And a lot of them are in the form of globular clusters. And a globular cluster is a cluster of hundreds of thousands to millions of stars that all formed about the same time. And they are very dense with stars. If you were on a planet in orbit around one of these stars, you would be able to read at night by the light of all the other brilliant stars close by in the sky. Still, so far, you could never travel to one, still that far. But we have these globular clusters in a spherical ring around us. It's very hard to see what our position is. And of course, in early times, they thought it sure seemed like we're in the very center of the galaxy. But actually looking at the position of all the globular clusters, we were able to come up with a much better estimate, which is roughly our current estimate of how far we are from the center of the galaxy. And again, that's crazy. You can hear bells going off when I say stuff like that. Come on over here and let me talk about the individual populations a little bit. Now, the halo stars I have drawn in yellow. Okay, if you see populations of stars in yellow, that means what about the stars? If you see populations of stars in blue, what does that mean about the stars? And the bulge stars are also a yellowish color. So yellow versus blue, what does it mean? Well, what is a blue star? Blue star would be a very hot, incredibly bright star, right at the upper left side of the HR diagram. These are very short-lived stars. So if you see on the disk blue stars, now it doesn't mean all the stars by any means are blue, but which stars are going to really color the disk? The brightest ones or the dimmest ones? The brightest ones. So the brightest ones are the bluest stars, and they live very short lives. Therefore, is star birth actively happening along the disk? Yes. Why? Well, if you also look along the disk in any good picture of the Milky Way or any other galaxy, you will see a beautiful galaxy like this. Along here, you'll see lots of signs of gas and dust, clouds of gas and dust. This is what makes stars. So it stands to reason if you have clouds of gas and dust, you're making brand new stars, and some of those are going to be blue. So anywhere that's happening, you will see a lot of blue. The disk is blue, so star formation is happening there. The bulge is yellow. So what does that suggest? Well, that indicates that star formation is not happening there. Those stars, the blue stars there, have all died in that area, and the only stars remaining are stars sort of like our sun, on the order of many billions of years old. Okay, so star formation has not gone on there for quite some time. Can we think of why? If I have a lot of stars very closely clumped together, is that going to put pressure on the gas and dust and get rid of those clouds that you need to give birth to stars? That makes sense. The other population would be the spherical population, very low density of stars, and also, like I showed on the other diagram, they're also yellow. So no star formation is happening in the halo stars. The disk stars, as they wander around, they just stay in the disk. They wander up and down as they go around. Our sun takes about 250 million years, on the order of 250 million years to go around once. And as it goes around the disk, it's never quite in the center, so it's always accelerating towards the center. Then it passes it and then stops, comes back up. So it's always wobbling back and forth, but gently going around. The one odd thing with the disk stars, things that it doesn't occur to you quickly, the disk is not a continuous object. They're not attached. Rather, the disk is a pressure wave moving through the interstellar medium, causing clouds to condense, causing the birth of new stars from these pressure waves as they move out through the disk. So if they were attached, as the disk spun, it would wrap itself completely up in them. So they're not at all attached. Rather, they are pressure waves moving through this. So now when you see a galaxy picture like this, looking at the colors, you can identify the processes, places where stars are forming, places where stars are absolutely not forming. That's galaxies, at least a first intro. That's our galaxy. We live in a spiral galaxy. Quite a few of the galaxies you see in space are spiral galaxy. But if I take two spiral galaxies and collide them together, like I'll show you with an animation I'll post on the Andromeda Galaxy, which is the nearest large galaxy to us, And the Milky Way galaxy in the future, they are anticipated they're going to collide. When the collision is all done, two spiral galaxies will have gotten together and formed a large, giant elliptical galaxy. Okay, large and giant are a little redundant. A giant elliptical galaxy. They are so mind-bogglingly huge. I should use other words other than just giant elliptical galaxy. They're really big. But two huge galaxies like ours and Andromeda make a much bigger galaxy when it's all done. So galaxies are constantly playing, and as they play, they change their forms endlessly. We started the universe off with galaxies that didn't have any real shape. Those are irregular galaxies. To me, they look a lot like bird poop. So just a mass of butt, and it looks like those birds were eating some blueberries. There's a lot of star formation in those galaxies, but there's no structure or anything to find. It's a mess. But if you start colliding those, what do you end up making? Very often you're going to make spiral galaxies with a bunch of those collisions. Some of the collisions, depending on how it works, can make smaller elliptical galaxies, but galaxy structure evolves like everything else. So galaxy evolution is a thing. Galaxies change over time. How do you know? Well, we're part of the change. When our galaxy first started, you didn't have stuff. You didn't have any stuff that you could make planets out of. In that galaxy evolution, you include us. So that's pretty cool. Even covered with chalk, this is one of the coolest things in the universe. Thanks for watching. Bye-bye, astronomy kids.